This is video 4 for the energy and power unit notes. This will be the final video for this unit. All right, this one we're going to finally start talking about power. And this is a very, very important concept. Energy, by and large, is something that doesn't exist. It's kind of weird to say this, but energy is something that scientists have made up to help us explain why things happen spontaneously. Power is something that's real. So let's go through this. To start off with, let's talk about a Big Mac. Big Mac has around 550 calories. And remember, this is food calories. One food calorie equals 1,000 scientific calories. So really, this Big Mac has 550,000 calories of energy. 1 calorie is 4.18 joules. You might have talked about this in chemistry. So this Big Mac actually has 2,299,000 joules of energy, about 2.3 megajoules. That's a lot of energy. All right, so using this then, my mass is 91 kilograms. If I were to eat a Big Mac and then release all of that energy at once, how high could I jump into the air? Okay, well, jumping means I have to do some work. So work equals the integral of the dot product of the force displacement vectors. I'm going to say it's kind of unrealistic, but I'm going to say it's a constant force. So this work will equal force times delta. I'll go with delta y since we're jumping into the air. And the force needed would be my body weight, so let's go mg delta y. So this delta y, how high I would jump, would equal my work or energy divided by mass times g. So if I were to release all this energy at once, theoretically I could jump 2,526 meters or 1.6 miles into the air. That is impressive. Why can I not do that? The reason is my body will not allow me to instantaneously convert all of my energy into kinetic energy. Won't do it. It will not allow me to do that. That process is regulated. And it's a very good thing it's regulated. If we were to spend all of our energy immediately, we wouldn't have any energy left over for thinking or powering our heart or breathing or anything else. This process must be regulated. We must not be allowed to expend all of our energy at once. So, because of that, we need to calculate the rate at which one form of energy is converted into another. And that's what power is. Power is the rate at which one form of energy becomes another. Classically, we say that power equals work divided by time. You could also say that power is the change in work or the derivative of work with respect to time. Or you can just simply say it's energy over time. Now the metric unit would be the joule per second. We call this the watt. And you might recognize this from light bulbs. Let's say we have a 50-watt light bulb. That means that light bulb is converting 50 joules of electrical energy into 50 joules of light and heat and sound energy every second. Now, in the US, we typically use the imperial system, and that's horsepower. And there's a handy little conversion. 1 horsepower is roughly 746 watts. You can, if you were to do some, estimations, you can say it's roughly 1 kilowatt. Because 746 kind of rounds up to 1,000. A top athlete has a power output of around 2 horsepower, and they can maintain that for a very short amount of time. So let's say I'm a top athlete. It's a stretch of the imagination. But let's say I'm a top athlete, and now let's recalculate my theoretical height I could jump using that power output. So, getting us started, we need to get everything in metrics. So 2 horsepower, that's going to be the same thing as 1,492 watts. I need a time. It's kind of guessing a little bit. Let's say it takes me half a second to do my jump. So, energy is power multiplied by time. So my energy then would be the 1492 watts times 0.5 seconds. So my energy I actually have is 746 joules. That's how much energy I actually have. So when I go to do my math, using the same formula as before, I would have 746 joules divided by my 91 kilograms and 10 newtons per kilogram. My delta Y now becomes 0.84 meters. That's roughly 32 inches. That's much more realistic. 40 inches is considered outstanding, and 50 inches is rare. Sometimes it's useful to make these calculations of power using forces. That gives me an opportunity to do a little bit of calculus. So power is the derivative of work with respect to time. Work is the integral of the force vector dotted with the dx vector. So that means that this power equals the derivative of an integral. Well, the derivative and the integral cancel each other out. So I'm left with this force dot dx over dt. And you may recognize dx over dt as velocity. We see that power equals the force vector dotted with the velocity vector. Or another way of writing this would be that power equals a force that is parallel to a velocity. Electric companies measure and sell energy. And that's kind of weird because energy is not really a real thing, but we can do that. So let's talk about how they calculate the usage. Well, power is energy over time. So energy would equal power multiplied by time. So in other words, the joule is the same thing as a watt times a second. Now that's a small unit. Electric companies typically use the kilowatt hour. And that is what energy is. So energy can be measured with calories, with joules, watt seconds, or kilowatt hours. Those are all units of energy. And there's even a specialized one called the BTU, the British Thermal Unit. Now, which is kind of fun, 1 kilowatt hour equals 3,600,000 joules, 3.6 megajoules of energy. And the average home uses roughly 30 kilowatt hours per day. The average cost is roughly 10 cents a kilowatt hour. So electricity tends to be very cheap, especially if it's created, or not created, but produced through burning coal. But other forms of energy are very pricey. Batteries cost a lot more than 10 cents per kilowatt hour, especially a AAA. AAA batteries and those little hearing aid batteries are very expensive per kilowatt hour. All right, well, this concludes the entire unit on energy and power.